Hello and welcome to another lecture. In this lecture we're going to talk about conjugated beam. The conjugated beam method, it's a good way to calculate a deflection and a slope of a deflected shape of a beam. So when you have the rail beam, this is the rail beam, then we produce a conjugated beam in a minute. In anywhere the slope is equal to the shear of the conjugated beam, and the deflection here at any point is equal to the moment at that point on a conjugated beam. What I mean by this, if I look at this right here, has a deflection shape like this probably. Come up like that, and it's going to go with the slope, and it's going to go like that. So now I have a deflection here, and I have a slope here. That will be the shear at this location, and the moment at this location of the conjugated beam. But how are we going to produce a conjugated beam? Let's go to work. One of the first things I want to do, I want to take a look at my rail beam, make a free body diagram. So I'm going to go ahead and come in. I'm going to erase these right here. And that's a roller, and that's a pin. So I'm going to go ahead and just basically replace them. I say, okay, this is going to be replaced with one of these, but we don't care about that. We're just going to care about AY for now. And it's going to replace this one with the BY. There's my free body diagram. But I want to know what my reaction at both points is. We've done this 1,000 times, and you learned this kindergarten anyway. We're going to go ahead and take a moment about point C to find out. Take a moment about point C. We're going to assume counterclockwise rotation. It's going to be positive, so it's going to be minus AY, which is going to rotate clockwise about point C. And it's going to be minus AY times 10 meters. And plus the load itself, 120 kilonewton, rotating counterclockwise towards C, and it's going to be times 3. And therefore my AY is going to go to 36. So I'm going to put down 36 right here, kilonewton. And this one is going to be 84 kilonewton right here. Make up your mind. 84 kilonewton. That's it. I need to draw the moment diagram for this. Then my moment diagram will become my conjugated beam. Take a look what I have on a PowerPoint. Where we have, let me bring it up actually. In a rail beam where we have a pin, in a conjugated beam will remain as a pin. And when we have a roller, it will remain as a roller and conjugated beam. However, when we have a fixed end in a rail beam, it becomes free end and there. So now look at right here. We have the like theta is equal shear, which is the slope, and a deflection delta or small v is equal 0 here, but over there is going to be the moment. And that's how we're going to take advantage of that. And if you go up to the next PowerPoint, we have these are the basically a table how you convert the rail beam to a conjugated beam. We're going to go ahead and calculate, do the shear moment diagram. I can't do the moment diagram right away, but I have to see the shear diagram before I get to moment diagram. And a lot of textbook, the example, they just go from here to moment diagram. Well, it's a little easier to do shear diagram. That way you know what you're doing. So now we have all the information we need. So I'm going to go ahead and drag all these points that I need right here. Okay. And I'm going to have, this is my shear diagram, Vx. I'm going to come up, let me just use a different color here. I had. See how blue will look like. So I'm going to go up 36 from here. That's a 36 kilonewton. And then nothing's going to happen. It's going to go across all the way here. Then it's going to drop 120. That was going to bring it to 84 here. Okay, and nothing's going to happen until it comes in right here and then goes back up to 0. This is a positive territory. The area of this is 36 times 7. The area of this one is 84 times 3. All right. So now the moment diagram, it's going to look like it's going to go up like this right here. That's a straight line, by the way. And then it's going to drop down back to 0. And this magnitude came out to 36 times 7, which is this is a 252 right here, this point right here. So this become 252, and this pair should come 252. 252. So it's going to go up 252, it's going to come back down to 0. Obviously there's nothing there, and then there's nothing. This is basically my moment diagram. So now I'm going to use this moment diagram to construct my conjugated beam. So this will be the load for our conjugated beam. Because this is a positive, and therefore the load's going to go up this way. And the magnitude of what's 252, it's going to be 252 divided by EI. And then we're going to look at the table that we have on a board, look at it. And you can see that where we have a pen, it's going to remain as a pen. And where we have an internal, we had internal right here, internal roller at the first problem. And this become hinge, and then the free become fixed. And that's how we construct it. Now we have this. This is easy because now all I got to look for, find the moment here. The moment right here, the deflection for me is equal moment over here, and theta is equal shear. So theta over here, this is going to be right here. It's going to be theta, and this is going to be basically my deflection delta or small v. And so this will become the moment over here, and theta is the shear. All we have to do calculate shear and moment. Piece of cake. And you thought it was going to be hard. I'm going to take a moment about point C, and if I look at here, because this is going up here, my reaction is going to be downward. I'm going to have a reaction down right here. It's going to. This is my new A prime y or AY, depending what you call it. So this will be my free body diagram. The reaction coming down because the load is going up. I got a hinge here, and that's a point B and point D. Let's figure this out. Let's take a moment about the summation moment about the hinge is 0, obviously. So we're going to take a moment. Summation moment about point C is equal 0. Counterclockwise is positive. So that's going to go clockwise. It's going to be AY multiplied by 7. 3 is 10. Then now I'm going to have two different, I got to break it down here. So the concentrated force for this one, let me move this out of the way. It's 252. Make it okay. So the concentrated force for this part is going to be right here. And then the concentrated for this force is going to be right here. And the magnitude for that one is going to be basically 1/2 times 7 times 252 divided by EI. All right? And magnitude for this one is going to be 1/2 times 3 times 252 divided by EI. So we're going to go ahead and take our moment. We're going to take a moment about point C. And that's going to be minus 252 divided by EI times 1/2 times 7. That's the magnitude of this force. And the distance is going to be 1/3 from here, so it's going to time 7/3, am I correct? Check my number, plus 3. Okay, 7/3, put it right here. And from here to here is 7/3, and then plus the 3 makes it that. And then I gotta have this one. It's gonna be plus, minus, I lied, minus 1/2 252 divided by EI times 3, and 1/3 of the distance from here makes it 2/3 of 3, so it's going to be 2. That's it, 2. 2, yeah. That is equal 0. So AY comes out to be, calculate that. See, I got a right number, I think I do. 546 kilonewton divided by E. We'll do summation Fy to solve this. Because this is a hinge, you can basically, we've done this before at the beginning of the semester. So you can break the hinge down, make it Cy and a Cx, and it'll be on opposite side, it'll be Cy and Cx. So this side is equal to that side. So since that is equal, so we're just going to go ahead and do summation Fy for the entire thing. I'm going to say summation Fy is equal 0. Going up is positive. You know what I'm talking about. And that's going to, we're going to find out what is the shear force right here. And then I want to find out what the moment is right here, because this is equal theta, this is equal deflection. So for the shear, it's going to be vertical. I'm going to have AY, which is a minus. That was minus, and let's just take the EI out. Let's say 1/EI. Get that out of the way. There we go. And let me use a different color so it looks nice. 1/EI. So I'm going to have minus 546. And I'm going to have this magnitude right here. It's going to be plus 1/2. I should have calculated that. 7 times 252 divided by EI. And then plus the other, this one right here, which is 1/2. 3 times 252 divided by, forget the EI, you have the EI. So let's take the EI out, I forgot about that. And no EI. And that's it. And plus this VD plus VD is equal to 0. So VD, which is equal to theta D, which is our answer, comes out to be 714 divided by EI. So in this problem, we don't have an EI. So E is 200 GPa, kilopascals, and I is constant of 262 millimeter by power 4. And therefore, my VD theta at point D is equal 714 divided by 200 times 262. So that gives me 0.0136. That's a radian, by the way. So that's one answer. Now let's find out what the moment is. So that will give me the deflection over here. So I'm going to come in, take a moment about point D. Summation moment about point D is equal 0, and add everything up. I'm going to have AY. It's going to be 546. Let's take out the EI just like last time, 1/EI. And it's going to be 546 going to be positive. So 546 times 7 and 3 is 10. 10 it is 15. And then we have this one, which is it's going to be minus 1/2 times 7 times 252. And that distance is going to be 7/3 from there, 7/3 from here to here, and then you have the 8, plus 8. Then I have minus the other part right here, minus 1/2 of 252. That's not a good 252. Let me write that better. Times 3. And then that distance from here to there was 2. 2 plus 5 is 7. Times 7. And then you have the moment itself. And that's going to be coming this way. So it's going to be minus md equals 0. So md, which is equal to deflection at point D, comes out to be 35, check my number, 3570 kilonewton divided by EI, which is basically 3570 divided by 200 times 262. You work with the units. If you get this right answer, that's a simple math. It becomes 68.13 millimeter or 0.068 meter. The answer should come out to 0.068, but you divide it by 1,000, you're going to get that. So this is how you find conjugated beam. Let me just go over it one more time, and then we'll be done. So we have the rail beam. This is the rail beam. An imaginary beam will be that one right there. In a rail beam, we just have right here, they asked us, what is the slope of this deflection shape, and what is the deflection here? So we said, okay, that's the rail beam. The slope at this location in a rail beam, it's the same as a shear at this location in a conjugated beam. And the deflection here in a rail beam is the same as the moment at the conjugated beam. But how we convert this to here, there's a table. And the table says if you have a pin here, you're going to have pin here. If you have an internal roller here, they become a hinge here. And also if you have a free end, it becomes a fixed end. So that's why we did. What about the load? The load, it's going to be the moment diagram for this right here, and that's the load divided by EI. This is a positive, that become positive. The rest of it is easy. Once you have this, all you have to do is find out the shear and a moment. And we've done this 1,000 times. If it was good, don't forget, give me a thumbs up. Take care.